If you will recall, yesterday we looked at the dot product. It showed up prominently in our line integral and our surface integral that we haven't even talked about. And the way we were thinking about the dot product, we could think of it as the amount of one vector contributing to the other vector. Now we're going to look at a specific example. Just like distance is equals rate times time is our favorite example in Calc 1. Work is equal to force times distance is our favorite example in Calc 3. So we're going to think of work is equal to force times distance. Work is equal to force times distance. If, however, our force and our distance are going in different directions, the distance is pointing in one direction, but the force is pointing in another direction. Then only part of this force is going in the direction of the dr. Only part of the force is going in the direction of dr. And like we saw yesterday, that part is going to be the dot product. So we're going to multiply that horizontal component of the force, or sorry, it's only horizontal because of the way I drew it. The component of the force parallel to dr is the magnitude of F times the cosine of theta. And we're going to multiply that portion of the force times the distance dr. So there's our distance, and here's our force. And so we see that the force times the distance, the amount of the force contributing to the distance dr in the direction of the distance. When we multiply these two together, we get work. So the magnitude of F times the magnitude of the distance times the cosine of the angle between them. And so that's F dot dr. So instead of just multiplying the force times the distance, and only some of the force is contributing in or is going in the direction of the distance, we find the dot product of the force and the distance. Let's make sure that we're doing this in a, well, I just made it clear. So let's suppose this is our force, 1I plus 2j. So if we think about what this looks like at every point, this vector field is pointing in 1I plus 2j. So this is what the vector field looks like. Now we're going to create a path. So let's define a path. Let's say C. Let's make C1 the path from 1, 1 to 6, 1. And I'm going to try really hard to not be annoyed that I put this third column of arrows 1/2 a square too far over. So if we want to calculate a line integral, we're going to need to parameterize our path from 1, 1 to 6, 1. Oh, the way we want to think about this is we're going to think of our vector field as the force and the path as our distance. That's the direction that we want to go. Now we can see as we're walking along this vector field, we're kind of getting the vector field is pushing this way. So it's going to take some effort on our part to stay on this path. So it'd be like, imagine yourself walking through the wind. The wind is trying to push you one direction, and it might be helping a little bit because it's generally pointing that way, but it's also pointing up. We need to know how much of this force is pushing us along this path. So let's make that calculation, see what happens. Let's parameterize the curve C. So we can parameterize the curve C. X starts off at 1 and ends at 6. So it'll increase by 5 in 1 unit. So I can say the X starts off at 1 and increases by 5. So when t is equal to 0, r of t is equal to 1. When t is equal to 1, r of t has a 6i. The j component is always going to be 1. The path was given to us, the parameterization we had to come up with. So here's our parameterization. The other thing that we need for the parameterization is the dr. We're going to create a line integral over C of f dot dr. So our dr will just be the r prime of t. The derivative in the x direction is 5. And the derivative in the y direction is 0. Our path, it makes sense. We got 0 in the j direction. We're not going anywhere in the j direction. Y coordinate is constant. Oh. Now we can set up our line integral. The integral over C1 of f dot dr. That's going to be the integral from 0 to 1 of the vector field f evaluated at r, but this is a constant 1i plus 2j, dot dr, which is 5i plus 0j dt. Work is equal to force dot distance. Because I need to know how much of the force is in the direction of the distance. In the dot product, we just get 5 plus 0. I forgot to write down the units, but the units don't matter. The force is in force units. The distance is in distance units. So the work is going to be in force times distance units. If the force is in newtons and the distance is in meters, then our work will be in newton meters. They're called joules. If our force is in pounds and our distance is in feet, then our units of work will be pound feet, because we didn't want to come up with more names for things, I guess. We, like I was there. If we think about force times distance, we look at the force in the horizontal direction. The force is a constant 1, and I'm going purely horizontal, so it makes sense that I got away with just multiplying the distance by the force. So let's suppose that I defined a new path. And let's just predict what would happen. Let's suppose that this new path Let's define a new path. C2 will be the path from 6,1 to 6,6. Let's predict what should happen. Come up with some expectation and then do the calculation to see if we confirm our expectation. Notice in the previous problem, or in the previous, with path C1, I got away with multiplying the distance by the force in that direction. Here I have a distance of 5 again, but my component of the force is 2. So that changes what we expect from our calculation. Either way, we need to come up with, we're expecting 10. So let's define another R of t. In this case, the x coordinate is a constant 6, and the y coordinate starts off at 1 and increases by 5 in 1 unit. And I just parameterize this from 0 to 1, just like before. Our choice of parameterization doesn't matter. Choice of path does. So our derivative in the x direction is 0, and our derivative in the y direction is 5. Now we can see where this is gonna, what's gonna happen here. Now when I multiply the j components, I have a j component of 2 from my vector field and 5 from the dr, 5 from the direction. So we're just gonna be multiplying the force times the distance. Although I forgot the dt again. So now our dot product is 0 plus 10. How's everybody okay? Super easy, barely an inconvenience. Let's take these two paths and put them together. Let's suppose that C3 is going to be a combination of these two paths. So we'll still have the same vector field. Let's say C3 is the path from 1, 1 to 6, 1, and then to 6, 6. So C3 is like a compound path. It goes from 1, 1 to 6, 1, and then to 6, 6. Notice that C3 is just made up of the two paths we had previous. C3 is just C1 followed by C2. So if we wanted to integrate over C3, I spelled 3 wrong. How many C's are in the number 3? 2, but they're backwards. Since C3 is just a path from 1,1 to 6,1, and then from 6,1 to 6,6, C3 is just a combination of C1 followed by C2. Just like we can with definite integrals, we can break up our line integral. In absence of any other instruction, this is what we would have tried first anyway. It's the first thing that would have occurred to us. If path C3 is just path C1 followed by C2, why don't we just integrate over C1 and then integrate over C2 and then add the results? It makes sense that we're just going to add the results because integration is just addition. And so we keep adding just over a different set. Questions? How's everybody okay? The thing we're trying to do is less about learning to make these calculations and more about building instinct about how the calculation should go. That's where our understanding is going to come from. I'm reminded of this because in trig, right now, I'm finally getting into trig identity. The reason I say finally is because I've done the 2 chapters after the trig identity chapter, but I didn't want to do it at the time. And so I'm like, well, I'm not doing this. I did a bunch of trig identities yesterday that I don't remember. The point is not remembering those trig identities. The point is doing the problems. That makes sense? This is why it's really easy to find answers online to any question that I could possibly ask. If it's not on chegg.com already, then it's about to be. I would be surprised if the entire calculus books haven't been translated so that you could just look up what the answers are. Maybe not by book, chapter, section, problem, but you could probably just find all the answers. That, of course, is not the point, but I also realize that we all can't afford to go to an Ivy League school and just buy ourselves a degree. So, got to be some way around it. Question? Let's build a different path. Same vector field. Let's make C4 will be the path from 1,1 to 6,6. Oops. In a quarter circle. So I'm gonna have the same starting and ending point that I had in the previous example, but I'm changing the path. So we still got the same starting and ending as we had for in the previous example. Same vector field, 1 plus 2j, starting off at 1, 1, ending up at 6, 6. But this time we're going to follow a quarter circle from 1, 1 up to 6, 6. Specifically this quarter circle. One of the things that we might want to notice is that the endpoints are the same as the previous example. If this vector field F happens to be a gradient field, then we won't have to do any work because we're starting and ending at the same point as the previous calculation. So if F is a gradient field, then we get away with doing no calculations, and we just say it's 15. So that's one of the things that we might want to notice right away. We got the same endpoints. If F is a gradient field, then the integral over C4 of F dot dr is equal to 15, since C4 and C3 have the same endpoints. We could just go through and find a parameterization for this curve and integrate. But we'll want to notice if that I picked specifically the same starting and ending point. This should make us wonder if F, this should make us recognize if F is a gradient field, then I won't have to do the line integral calculation. It's just going to be 15. But I do have to know if F is a gradient field. So let's find out. If fx of xy is equal to 1, that means f of xy will have to be 1x plus some function of just y. Well, I shouldn't call it f. Don't use the same letter for all your functions. Don't do George Foreman math. Just give them all the same name. So it'd be some other function of just y. So we integrate with respect to x, but that means any function of y is also a constant. So if fy is equal to 2, because we're supposing that f is a gradient field, then f should be 2y plus some function of x, because function of x will be constant with respect to y. So it looks like f at xy could be x plus 2y. Derivative with respect to x is 1, the derivative with respect to y is 2. So f is a gradient field, and this is the potential function. Therefore, the line integral on any path from point P to point Q will be the same. Questions? Moreover, we should be able to use the fundamental theorem of calculus for line integrals. If I say 1, 1 is P and 6, 6 is Q, then F at Q and F at P is 1 plus 2 times 1, 3. And so the integral over C4 of F dot dr will be just F at Q minus F at P. Any questions? How's everybody okay? Super easy calculation? Calculations aren't the thing. Thinking is the thing. Moreover, we should be able to parameterize this curve and come up with 15 by calculating the line integral. We're going to have to figure out a way to get a circle of radius 5 with the center at looks like 1, 6. If we parameterize this curve, we should get the same thing. We should still get 15. We know we can not trying to hide stuff. We know we can parameterize a circle with x equals cosine t and y equals sine t. This will start off at 1, 0 and then go around once counterclockwise. If I want to increase the radius, I just need to increase the amplitude of the cosine and the sine. 5 cosine t, 5 sine t is going to make a circle of radius 5. If I want to move the center to 1, 6, I just move the middle of my cosine graph to 1, and I move the middle of my sine graph to 6. Now, the other thing is, if I just have t running through here, I will get this whole circle, and I don't want the whole circle. But at least it's going in the right direction. I'm only going to want this quarter circle down here. So t equals 0 is going to start over here at well, this left point, and it's going to go around to pi over 2, pi to 3 pi over 2, and up to 2 pi. That'll give us that quarter of the circle. Change the amplitude, change the radius, change the vertical shift, change the center. We need r prime to be our dr. The derivative of cosine is negative sine, and the derivative of sine is cosine. So our integral our line integral, well, I'm not going to be able to talk into it. That's right. Our line integral will be the vector field, which is constant, evaluated at the points on the curve C, dot the dr. So we're still integrating. We haven't integrated yet. And I find the dot product. So -5 sine t plus 10 cosine t dt. One time, the i's 1 times -5 sine t, and for the j's, 2 times 5 cosine t for 10 cosine t. We're going from 3 pi over 2 to 2 pi. So we can see that the sine is going to give us a 1, and the cosine is going to give us a 1. And we'll add, sorry, the sine is going to give us a -1, and the cosine is going to give us a 1. Any questions? Derivative of cosine is negative sine, derivative of sine is cosine. Any questions? We didn't have to do this because we had previously recognized that we had a gradient field, but it's important to be able to do the calculation anyway. We got 3 ways we got to do this. Gradient field, and we just used the previous answer because we had done it before. Since it's a gradient field, we were able to use the fundamental theorem of calculus, or we were able to just go through the problem by parameterizing the curve. All right, that's going to do it for today. I will see y'all on tomorrow.